We live in a world, a reality, ruled by straight lines. Our streets, houses, cubicles, the shelves in our closets, well, not my closet, but virtually all of our space is parceled into rectilinear grids. Mathematicians were also ruled by straight lines, some would say imprisoned by them, for 2,000 years. But what is a straight line? And when is a straight line not straight? Could it be when you live in a curved world? These questions are at the heart of one of mathematics' most mind-bending revolutions, a revolution that created whole new geometries and whole new worlds. The world is filled with an immense variety of shapes and structure. We use geometry to describe this physical space. Lines, points, angles, and numbers characterize, organize, and transform the shape of the world, even of space itself, into coherent ideas. The word geometry comes from geo, meaning earth, and meter, meaning to measure. And anyone who sees the pyramids knows that the ancients knew how to measure a straight line. Much of early mathematics was all about geometry as well as simple computation, and it was largely developed for trade, agriculture, and building. But mathematics was also linked to religious observances, the motions of the planets, and the construction of calendars. For the Greeks, mathematics was all about the tangible, things we can see and touch, things that are real and measurable. Aristotle, in fact, considered even physics to be subservient to mathematics, believing that perfect motion had to take the form of the perfect geometric figures of straight lines and circles. The paradigm of this geometric outlook lies with the great Euclid. With one monumental work, Euclid set the stage for how we look at and measure the world geometrically. Except there was a flaw, for there are more than circles and lines in our universe. In his book, The Elements, Euclid gathered all the theorems of his day into a framework of basic theory and proofs. In it, he laid down 5 postulates and invented a method by which we can prove geometry's most basic truths. And it all starts with 2 points in a line on a piece of paper, a 2-dimensional plane. Now, the first 3 postulates are simple enough. The first states that a straight line segment can be drawn joining any 2 points, just like that. Now, the second says any straight line segment can be extended indefinitely in a straight line. The third states that given any straight line segment, a circle can be drawn having the segment as radius and one endpoint as center. The fourth states simply that all right angles are equal, and we need this so that we're sure that the space we're working in is essentially the same everywhere. But the fifth is not so simple because it deals with the nature of parallel lines. It goes something like this. Suppose a line segment intersects 2 straight lines in such a way that 2 interior angles on the same side add up to less than 2 right angles. Then the 2 lines, if extended indefinitely, must meet on that side on which the angles sum to less than the 2 right angles. Now that sounds logical. In fact, so logical that mathematicians actually believed that it wasn't so much a postulate, that is, an assertion about geometry that was independent of the other 4 postulates, but rather that it was a logical consequence of the other postulates. In other words, mathematicians seemed sure that all we needed to know was in those first 4 postulates, and that anything else could be derived from them. So for 2,000 years, mathematicians tried to prove that 5th postulate from the other 4, and they failed. It became known as the scandal of geometry. But why? Well, again, implicit here is the idea of parallel lines. For what happens if those interior angles do add up to 2 right angles? Then the lines must never meet. Well, maybe. The truth is that there's more than one kind of geometry. You see, we don't live on a flat world. We live on a curved one. It's just that it's not obvious to us, at least not from where we're standing. If a man's walking on a surface, then for all he knows, he's on a plane. Locally, his world is flat. But if he's really on a curved surface, how does he know he's on a curved surface? From the point of view of just looking, he doesn't. So for the Greeks, mathematics was largely about the geometry that they could see and measure in a rational way. So straight lines, right angles, parallel lines, those all seemed rational and measurable and seemed to be the ones that they wanted for the flat world. And even though they knew the world was round, it wasn't something that they could measure with a ruler, and so they ignored it. Logically, the 5 postulates made perfect sense. But from time to time, mathematicians challenged that 5th postulate, even as early as the 5th century. But it wasn't until the 19th century when 3 mathematicians finally proved that there were indeed worlds out there and geometries that may seem impossible, but obey logically consistent laws. In other words, the 5th postulate was independent of the other 4. One of those 3 mathematicians was Carl Friedrich Gauss. Gauss, a professor at the University of Göttingen in central Germany, was known even in his own time as a great mathematician. Napoleon's armies spared his town simply because he lived there. Today, he's mentioned in the same breath with Archimedes and Isaac Newton. In 1822, Gauss was hired to conduct a survey of Hanover and make a map of the German countryside that would connect to an existing map of Denmark. Naturally, he was faced with the challenge of making a 2-dimensional map from 3-dimensional data, affected not just by changes in elevation, but by the curvature of the Earth. Because he was a surveyor, he knew that measured over great distances, a triangle's angles do not add up to 180 degrees. But he also knew that the 180-degree rule was the equivalent of the 5th postulate. It is at this point that Gauss made one of those leaps of intuition that have often propelled mathematicians to whole new understandings of our universe. Gauss knew a triangle doesn't add up to 180 degrees in a curved world. This led him to wonder if space itself were curved. What if he threw out the 5th postulate? Gauss realized that there exists a whole different kind of geometry, one that moves beyond flat Euclidean space into curved spaces. He was so unnerved by this realization that he didn't publish it. And by not publishing, Gauss muddied his legacy, because within a few short years, the mathematicians János Bolyai and Nikolai Lobachevsky both came up with a similar geometry, what they called absolute geometry, because it was established without Euclid's 5th postulate. Still, the geometry they described was complicated, and it took the mathematician Bernard Riemann to think about this problem differently. He asked a more basic question. Can I characterize a world where curvature is the same everywhere? And he did this using Gauss curvature. Instead of looking at triangles on a surface, we look at circles. If we use a piece of string of length r to trace out a circle on a flat surface, we know that we get a circle whose circumference is 2 pi r. But if the surface is negatively curved, we get a number greater than 2 pi r. And if it's positively curved, we get a number less than 2 pi r. The discrepancy between the circumference of a circle on a curved surface and the circumference of a Euclidean circle of the same radius can be used to define curvature. With this notion of curvature, Riemann was able to classify surfaces of constant curvature, whether it be positive, negative, or 0. I'm here with Dinah Tamanya, adjunct professor of mathematics at Cornell University and an expert in helping people visualize non-Euclidean geometries. Dinah, let's try to show people the distinctions between flat space and curved space.
Here we have a flat paper, which can be a representation of our usual Euclidean geometry.
Right, or a map, for example, right?
Yes, it can be like something flat. And here we are having a globe, which is a representation of the sphere.
Right, curved space.
Yes, and if our geometries would be the same, then we should have no problem of wrapping this paper around the ball, like we are doing it with the presents.
All right, well,
let's try.
Let's give it a shot.
Let's
roll it around.
I think that's...
Roll it around. Yes, another perfectly wrapped birthday present. All right. So we've got some places which are flat.
Some places are flat, but then it gets too much, and then this is not very nice. Doesn't look very nice, so can't really put it on. Once we are
actually
opening,
seeing something quite fundamental, which is that flat space cannot go directly onto a curved space. There will always be some problems.
Yeah, and those are the problems which map makers since ancient times have encountered. How to represent this curved space on a maps. So it means you have to decide what you are preserving, because there are different ways of making maps. You can preserve kind of like an angles, or you can preserve like a proportions between distances.
But you can't do both at the same time.
No, you can't.
There's always going to be some scrunching, just
there
like
is
we've
something,
seen here.
yes, and that scrunching happens because this is different curvatures. Because our flat paper had 0 curvature, and this one is constant positive curvature.
Right. This representation can't both be distance preserving and angle preserving.
Sure.
Is that right?
Yes, because like flat maps, that's a Euclidean plane.
That's right.
And if we want to travel, especially when we are doing air travel, so we have to take in account that our Earth is more like a sphere.
So let's think about a potential travel plan. I'm in Seattle and maybe I want to go to London,
Good.
for example.
Okay.
So there's Seattle over there and there's London
yes,
over there.
in the Euclidean plane, it would look like a straight line. We were
Famous
seeing
saying,
like
the shortest distance between two points is a straight
line. Let's see what happens on a sphere.
And so now the shortest path, I can imagine, think of that as a string, and I want to think of using the least amount of string that's constrained to be on the globe. Is
yes,
that right?
It should be on a circle, and
That's right.
that is an arc of a great circle.
An arc of a great circle, which is sort of like an equator that's at an arbitrary
Yes,
place.
it can be at any places. And now you see the difference between, now you have 2 points, your Seattle and London, which is connected with 2 straight line segments on a sphere.
Right. There's the short one.
There is a short one, there is a long one. So therefore we can see that shortest and straight is not the same on a sphere.
That's right.
It's another difference between two geometries.
So now we've seen 2 kinds of curvature. There's positively curved space like the sphere. There's flat space like this tabletop. But in fact, there are negatively curved spaces, and they're very mysterious and interesting, like hyperbolic space. So let's take a look at one.
I'm Martin Steiner. I'm at the University of North Carolina. I'm a research assistant professor both at the Department of Computer Science and Psychiatry. And this is, of course, kind of like a weird association. What has psychiatry to do with computer science? What we're doing here basically is neuroimaging.
Okay, so what I'm showing you here is a movie of the average brain as a function of age. Now this is human brains, they're all healthy, and you can see that at the beginning it's age 30 and at the end it's age 70, so they're all adults. What I want to do is show what are the essential changes in the brain as a function of age. And so now what you can see is I've taken all of the images of the real subjects, now these are real subjects, not averages, and put them together in this movie that shows you the amazing amount of variability you see in the shape of the brain, even between healthy subjects. Now, what you're looking at here is this nonlinear shape space, and the idea is that we want to compute the mean on this curved space rather than in Euclidean space. And so what we have to do is have a notion of centrality that I'm depicting here, where this is the average that we're going to compute, and it's going to minimize a sum of squared distances on this curved manifold, and that's how we define the average.
Using all of the brains
that we've collected.